Namaste, welcome back to Sthipragna channel and you are watching Machine Learning Basics Theory Lectures. So far we covered I guess 6 videos, 6 topics, and our last topic was on neural network. I hope you enjoyed it. And since we learned about the neural networks, I felt like okay, let's cover different types of the neural network algorithms that we have out there. Okay, and those are RNN, recurrent neural networks, LSTM, long short-term memory, and then GRU. So what are these three? We will go in 3 different videos, but this video we are going to learn about RNN, or recurrent neural network. What is it exactly? The RNN is a type of neural network designed to handle sequential data. Okay, what is it designed to handle? Sequential data, where the order of data point matters. What does it mean by order of data points matters? Sometimes what happens is the data points that you are giving or the input that you are giving, it has to have the order preserved. If you don't have the order, then they will be messed up. Correct? If there are, let's say, in your data points, the data point says something about step 1, 2, 3. If you don't maintain the step, if you process the step 3 first, step 2 first, and then so on and so forth, then of course whatever you are going to predict is going to be wrong. So you will use RNN where the order of the data point matters, because it's going to handle this sequential. It is designed to handle sequential data. Unlike the traditional feed forward neural networks, which process inputs independently, RNNs have connections that form cycles, allowing them to maintain a memory of previous inputs in the sequence. This memory is crucial for tasks where the context of earlier inputs is necessary to understand later inputs, such as in language processing, time series analysis, and more. So basically, during that scenarios, we will use recurrent neural networks, because this is a high level architecture of it. But how does this work? Okay. Sequential processing. RNNs process input data one step at a time, maintaining a hidden state that is updated with each new input. Okay, if you look at here, you can see input layer, then hidden layer, then output layer, which is what we're talking about. And the hidden state is essentially the memory of the network. It captures information about the previous steps, previous time steps, which is then used to influence the prediction or output for the current time step. And then you have something called weight sharing. Remember, we have spoken about weights as well. RNNs share the same weights across all time steps, which allows them to generalize across different parts of the sequence. However, standard RNNs struggle with learning long-term dependencies due to issues like vanishing gradient problem, which is why architectures like long short-term memory and gated recurrent units were developed, which are our next 2 videos. We will talk about it. Those are the challenges, long-term dependencies, and so in order to handle that one, we have LSTM and GRUs. So if you look at some real life examples, we can use them in language modeling and text generation. What is the scenario? Predicting the next word in a sentence. RNNs can be trained on large text corpora to predict the next word in a sequence of words. For example, given the input, the cat is on the RNN might predict mat as the next word. Cat is on the mat. So what are the use cases? Autocomplete in text editors or search engines, correct? Whenever you are trying to search something in Google or anywhere, you will get autocomplete, right? So here behind the scenes are these days wherever you type something, it either auto completes or it auto corrects it. So behind the scenes they are using RNN. And you can also use this in sentiment analysis. Let's look at the scenario. Determining if a review is positive or negative. An RNN can take a sequence of words from a review and output a sentiment score or a class label, like whether it is positive or negative. The network considers the entire sentence structure to make this prediction, leveraging the context provided by earlier words in the sequence. So use case again, analyzing customer reviews on e-commerce platforms to determine overall product sentiment. And time series forecasting. predicting future stock prices or weather conditions. An RNN can be trained on past behaviors like previous stock prices to predict future values. The RNN's hidden state allows it to remember trends and patterns over time, making it well suited for such tasks. And the use case, financial forecasting, weather prediction, demand planning, and so on and so forth. And speech recognition scenario, converting spoken words into text. RNN processes an audio signal as a sequence of sound waves, converting it into a sequence of phonetic representations and then into words. The sequential nature of speech makes SNNs particularly useful for this task. Example, you might have already heard about this. Voice activated assistants like Siri and Alexa might be using RNN behind the scenes. Okay, so that's about RNN. Now let's go and jump into our step-by-step explanation of RNN using a example scenario. All right, so what are we using? Which scenario are we using? We are using the sentiment analysis. Okay, we are using sentiment analysis scenario that we have spoken earlier. Determining if a given text, let's say a product review, is positive, negative, or neutral. Okay, and the example text we are taking is, let's say, I love this product, it works great. Okay, so that's our review. Now our task is to classify the sentiment of the text as positive, of course, right? I love this product, it works positive, it works great is a positive sentiment. Now what are the steps that we will take all the time? We will prepare the data first. Prepare the data. Now, since this is a text, what will we do? We'll do text pre-processing by how? By tokenizing. We have done exactly same thing for another examples as well. We will split the text into individual words, or we call them as tokens. Example for this would be, once you convert or tokenize it, you will have a list of words, I, love, etc. Usually you will convert all of them either to lowercase or uppercase, and then you will remove any punctuations which we don't need, correct? Like for example, comma, etc. And then we will assign an index to each unique word. Okay, so that would become like this. I love this product, it works great. We will assign an index to each of the words. And once this is done, what will we do? Preparing as part of the pre-processing the data, we will convert the text to numerical data. How do we do that? By using this particular one, we just indexed it, and then we will create input sequences. What is an input sequence? It's a sequence of word indices representing the sentence, and our example indices are these. And the next step is building our model. Correct? Our text preparing the data is done, our pre-processing, our text pre-processing is done. Now it's time to build our RNN. And remember, what are the layers we had? We had input layer, hidden layer, and output layer. Correct? Input layer receives our input sequence, which is 1 to 7, and the hidden layer processes each word in the sequence, updating the hidden state at each time step. And outputs a sentiment score or score label after processing the entire sequence. Okay. Then after building, we are going to do what? We are going to train our RNN. Okay, let's look at our step by step. First, what happens? Forward propagation. As part of forward propagation, time step 1 would be, as you can see here, time step 1, it will process I, which is index 1, and then it will update the hidden state. And then time step 2 will process love, which is index, and it will update the hidden state, so on and so forth. Then it comes to time step 7, which processes great at index 7 and outputs the sentiment, because that is the last word. And what is so far you see nothing outputted, because it still has more words to come. So since this is the last word, it will output the sentiment as positive. So you can see how it goes here. And this is forward propagation. Remember, we have for our forward propagation and then backward propagation. Backward propagation, what do? You will calculate the error between the predicted sentiment and the actual sentiment using cross entropy loss. And then based on the error, you will adjust the weights, and I mean it will automatically adjust the weights and biases to minimize the error, propagating the error backward through time. Usually that's what you do, but here I guess we are good. And then you will evaluate the model. You train the model, then you will evaluate it, the final step, correct? Evaluating on our test data, we will use a test set of labeled reviews to evaluate model accuracy. And let's assume that test data happen to be like this, correct? So if you see, these are the actual positive, negative, and neutral, and those are the predicted positive. So 50 out of 50 positive, those were actuals and predicted, and you can see the numbers. Okay, and then if you scroll down, you will see the accuracy table. Okay, training accuracy. So epoch, what is the epoch? They are like iterations, right? The first iteration, your accuracy, training accuracy was this, validation accuracy was this. As you can see, the more number of iterations, the more accurate the model became, and the validation accuracy also improved here. So that is shown in this particular graph. So what are you seeing here? Epoch 1, as you can see, the model starts with relatively low accuracy, which is somewhere here, it's not even showing, indicating that it is just beginning to learn patterns from the data. And epochs 2 to 5, steady improvement as the model adjusts its weights and biases through training. And epoch 6 to 10, the accuracy continues to improve. If you look at this one, I'm assuming 10 is what? Accuracy 85.8 somewhere here, or this one, I guess. Okay, I think it's black, it's not visible, but you see it, right? So both training and validation accuracy increase over epochs, demonstrating effective learning and generalization. Okay, so that's what we plotted here. Epochs on the x-axis and accuracy on the y-axis. So this is our accuracy table. Now let's look loss over time. Okay, loss over time, you have two losses. One is the training loss and then the validation loss. Just like you can see here, we have training accuracy and validation accuracy. Training loss indicates how well the model is fitting the training data, and validation loss indicates how well the model is performing on unseen data. So this is sample for the one that we just used. So you can see as the number of epochs increase, the training loss decreases and the validation loss as well decreases. And then we made a plot similar to the accuracy, which looks something like this. Epoch 1, high loss values, you can see here, indicates that the model's predictions are far from the actual values. And then 2 to 5, significant reduction in loss as the model learns from its errors and adjusts accordingly. And then 6 to 10, loss continue to decrease but at a slower pace, suggesting the model is converging. Both training and validation loss decrease over epochs, indicating improved model performance and reduced errors. So that's about the accuracy and the loss plots. And the conclusion, what is the conclusion for this? So here we saw how well the model learns over time, and if validation metrics diverge from training metrics significantly, and adjusting parameters like learning date, batch size, and model complexity based on the trends observed. And overall, by plotting and analyzing these graphs, you can make informed decisions to improve your RNN model's performance in sentiment analysis tasks. So most of these algorithms, they kind of seem same, but I guess when we code, they will look different, because all the algorithms, you will prepare the data, and then you will build the model, then you will train the model, then you will evaluate the model, correct? So those are the steps, and each one it differs of course based on the data, but like for example like pre-processing and etc. But overall these are all the same. So this is about the recurrent neural networks, which is one type of or one model of neural networks. Then we will see the long short-term memory neural network. I hope you enjoyed this video. If so, don't forget to like, comment, and subscribe to this channel. See you in the next video. Peace out.